Okay.
Yeah.
Gaurav, it's not recording yet. Since number theory seminar, our speaker today is Professor. It's not recording yet.
Yes.
Something wrong. Hang on.
I can see the screen, the file in my screen.
It says it's recording. Just hang on a second. Yeah, it is recording. Go ahead.
Okay. Good afternoon, everyone, or rather, good evening, everyone. So we are delighted to have Professor Ayyadurai Sankaranarayanan as our next speaker in the Special Functions and Number Theory seminar. Professor Sankaranarayanan is a well-known analytic number theorist. He did his bachelor's and master's from Madurai Kamaraj University and followed by a PhD at TIFR Mumbai, where he worked with Professor K. Ramachandran as his PhD supervisor. For many years, he was at TIFR Mumbai as a professor, and currently he is in the School of Mathematics and Statistics at University of Hyderabad. So he has visited here at IIT Gandhinagar, and we had a very nice time discussing mathematics and many other things. And I'm sure many people in the audience would be of the same opinion, getting a chance to work with him. So today we'll get to hear from him on the Rankin-Selberg L function related to the Vardaman-Jacquet L function. Over to you, Professor.
Okay, thank you very much, Atul. And I thank the organizers, particularly Professor Atul Dixit, Gaurav Bhatnakar, and Professor Rajkumar for arranging my talk. And today's talk is about the Rankin-Selberg L function related to Vardaman-Jacquet L function. Next screen, please. So this talk is split into 4 or 5 parts. So I give some introduction to the subject matter, then some preliminaries, then whatever the lemmas I need, I explain, and then I go to the asymptotic formula for the kth reason, what I wanted to do here. So next screen, please. Okay, definition 1. N is an integer greater than or equal to 2, and V is the tuple V1, V2, Vn minus 1 in the space C power n minus 1. The mass form for SL and Z is of type V, which is a smooth function F, the square integrable function in the space as SL and Z mod H power n. H power n is the hyper upper space, n-dimensional hyper upper space, which satisfies these 3 conditions. The first condition tells you that F is invariant under SL and Z here, and for all points Z in the H power n. And D is an operator in the center of the universal enveloping algebra, GL and R, for which this F behaves like an eigenfunction for this operator. That's what it means. And the third condition is that the integral over the space SL and Z intersection U modulo U, F of U Z dz is 0, which happens for all upper triangular groups U, and U contains each element is a matrix, certain matrix, upper triangular matrices. Yeah, and the diagonal entries itself is a matrix. These are all R1 cross R1 identity matrix, R2 cross R2 identity matrix, and RB cross RB identity matrix. The diagonal entries in such a way that R1 plus R2 plus etc. RB is N. This is the condition for a mass form related to SL and Z of type V. Okay, next screen, please. A Hecke mass form is a mass form which is an eigenvector for the Hecke operator algebra. Hecke operator algebra is nothing but the set of all Hecke operators in this case. So hereafter, our FZ is a Hecke mass form of type V, V is the tuple V1, V2, Vn minus 1, the space C power n minus 1 for SL and C. Then one knows that F has the following Fourier expansion with multiple sum, and you have this normalized coefficient, and Fourier coefficient is AF M1, M2, etc. M1 minus 1, and here you can see that the summand, this summand runs from M1 from 1 to infinity and etc. And the last one M1 minus 1 is different from 0. Of course, it runs over non-zero integers. And here gamma runs over the elements of this set U n minus 1 z. U n minus 1 z is nothing but the upper triangular matrices of order n minus 1 cross n minus 1 with integral entries, and of course SL n minus 1 z, one with its square matrices of order n minus 1 cross n minus 1 with integral entries with determinant 1. And here Wj is the Jacob-Whittaker function, and this function acts on certain quantities. Next slide, please. Next page, please. Hello. Next page, please.
Yeah, it is the next page. One more.
Oh, yeah, one more. This I have finished. Fifth page.
It's on the top of the page which you want to.
No, the next one. This is the fourth page, I suppose. Fifth one.
This is seventh page already.
Okay, fine. Next one. Oh,
This is fifth.
no, I could see only fourth page here.
Okay, I'm at the fifth page, and the rest of us can see fifth page.
I couldn't see the fifth one here.
Atul, do you want to chime in? Let me try it again. I'll share it again. Can you see?
Yes, but yeah, okay, that's fine. This is the fifth page, that's fine.
Okay.
Yeah. So here, M is the diagonal matrix with the diagonal entries are, the first entry is M1, the product M1, etc., Mn minus 2, modulus Mn minus 1, and the lowermost entry is 1. This is the way the diagonal entries are there. And the character function psi 1 1 epsilon acts on the upper triangular matrices. Of course, the diagonal entries are 1 1, and the upper entries are integers. The just above the diagonal is u1, u2, un minus 1, and this acts in the manner that this is nothing but e power 2 pi u1 plus u2, etc., un minus 2 plus epsilon times un minus 1. This is the way the character function acts. Next page, please. Okay, so given a mass form F,
You're muted now. We can't hear you. Sorry, we can't hear you.
I guess there is some network issue from his side.
It's okay. Could you please hear me?
Yeah, now we can.
Okay. Okay. So the dual form F tilde is nothing but F of W dot Z inverse transpose and W. Here W is the cross diagonal matrix with these entries. This is called this F tilde is called the dual form of F, which is nothing but a mass form of the reverse type Vn minus 1, Vn minus 2, etc. V1 for SL and Z. The main point here is that whenever you have the mass form F for SL and Z with Fourier coefficient AF, M1, M2, etc., M1 minus 1, the dual form F tilde will be having the Fourier coefficient AF, Mn minus 1, Mn minus 2, etc. This is the important point one should notice. Next page, please. Yeah. One notices that this Fourier coefficient AF, M1, M2, etc., Mn minus 1, this satisfies the multiplicative relations, namely AF M1, M1 prime, M1, M2, M2 prime, etc., Mn minus 1, Mn minus 1 prime, which is nothing but the product of these two Fourier coefficients, as long as these two products are co-prime. M1, M2, Mn minus 1, and M1 prime, M2 prime, Mn minus 1 prime, these integers are co-prime. Also, one observes the following multiplicative relation, namely AF M1, 1, 1, etc., AF M1, M2, Mn minus 1, this product satisfies such a multiplicative relation, and this Fourier coefficient AF M1, M2, etc., Mn minus 1 conjugate is nothing but the reverse one. That is the coefficient of the dual form. Fourier coefficient of the dual form. Next place, please. Next page. Yeah. The next definition, what we want to make here is that Godemann-Jacquet function, which we call it LFS attached to F, which is defined for real part of S is bigger than 1, which is nothing but the Dirichlet series sigma m equal to 1 to infinity A of M 1, 1, 1, etc., divided by M power S, and which has the Euler product, namely the product P. This P runs over all primes P, and product I is equal to 1 to N, that is the dimension or whatever you call. 1 minus alpha pi p power minus s inverse. Here, this alpha pi are certain complex numbers. For I is equal to 1 to n, these are the complex roots of the monic polynomial given here with complex coefficients. Yeah, and these are the Fourier coefficient with these components are written first r minus 1 components are 1, rth component is p, and the rest of the components are 1. And one observes here that this Fourier coefficient, this particular Fourier coefficient is nothing but the sum of the products of all these alpha pi's, where I1, I2, IR, this component is 1 less than or equal to I1, strictly less than I2, etc., strictly less than IR, less than or equal to 1. This is true for all R between 1 and n minus 1. Okay, next page, please. So taking logarithmic derivative of the L function LFS, one observes here that minus LF dash divided by LFS is nothing but the Dirichlet series with the coefficient lambda m. This is the von Mangoldt function. AFM is another multiplicative function. This AFM multiplicative function satisfies the following relation, namely at any prime power, AF p power j is nothing but the sum I is equal to 1 to n alpha pi power j, and this is true for all integers j greater than or equal to 1. The important point here is that Rudnick and Sarnak introduced the following conjecture, namely for any fixed integer j greater than or equal to 2, if you consider this sum, their conjecture says that this sum is finite. One should notice that this Rudnick-Sarnak conjecture is true as long as n is less than or equal to 4, and this is due to Kim and Sarnak and Rudnick also. These two papers are given in the references. And next page, please. So for n greater than or equal to 5, you don't know whether this conjecture is true or not. Okay, still open. Next definition is that given any two mass form for SL and Z, F and G, with type VF, VG respectively, one has the Fourier expansion for F in this manner, and Fourier expansion for G you have in this manner. Then the Rankine-Selberg function, in this case related to F and G, is defined to be the product of the Riemann-Zeta function at NS and this multiple Dirichlet series. One observes that this Rankine-Selberg function defined just now is absolutely convergent as long as the real part of S is sufficiently large. Next page, please. In the special case when G is equal to F, indeed this Rankine-Selberg related to F and F, which we denote by L, F cross Fs, which is nothing but the product of this Riemann-Zeta function along with this multiple Dirichlet series, whatever you call. And the main point here is that this Fourier coefficient AF, Fourier coefficient, whatever it appears to square, which is actually non-negative. This is very, very important. Fine. So what we do here is that for real part of is sufficiently large, you know that this Rankine-Selberg function is absolutely convergent. So we write in a simple way that this Rankine-Selberg function has the normal Dirichlet series sigma m is equal to 1 to infinity bm by m power s. Bm is certain coefficient which depends upon this product representation in principle. Okay, next page, please. So for n greater than or equal to 2, regarding the Euler product, whenever F and G are two mass forms for SL and Z, you have LFS to be such an Euler product one has, and for LG also Euler product, similar Euler product, and the LF cross G is having the Euler product, namely this one. From here itself, one can observe that the Rankine-Selberg function is of degree n square, n cross n. So this is of degree n square. Next page, please. All right. So regarding the functional equation for the Godman-Jacob L function LF and LG, if you define lambda Fs to be this product times LFS, then the Godman-Jacob L function LF satisfies the functional equation lambda Fs equal to lambda F tilde of 1 minus S. Similarly, such a functional equation holds good in the case F is replaced by G. Of course, lambda Gs is equal to lambda G tilde of 1 minus S. And of course, these are all certain gamma factors you have. And from this gamma factor also, one can decide the degree of the corresponding L function. In this case, for the Godman-Jacob L function, the degree is n, and in the case of Rankine-Selberg L function, L F cross G, in this case, F cross F or F cross G, it is going to be the degree n square in principle. Okay, next page, please. So one knows that given two mass forms, F and G of type VF and VG for SL and Z, the Rankine-Selberg function has a meromorphic continuation to the whole complex plane with at most a simple polarity is equal to 1 with the residue, which is constant times the Petersonian inner product of F and G. And also this Rankine-Selberg function satisfies such a functional equation. If you define lambda F cross Gs to be this double product with this quantity times L F cross Gs, then the functional equation reads as lambda F cross Gs is equal to lambda F tilde cross G tilde of 1 minus S. From the theory, one knows that this particular product is nothing but pi power minus ns by 2, and this double product of this quantity is pi power minus n square s by 2. The whole point here, what I want to make is that this functional equation somehow resembles the functional equation of the Riemann zeta function, except for this conversion factor in principle. Okay, next page. So what we do in the whole talk is that we assume G is equal to F, and F is a self-dual mass form. That means that F is equal to F tilde. Then the functional equation takes the shape delta of F cross Fs is nothing but this pi power minus n square s by 2, and then this double product. First product runs from 1 to n, and the second product j runs from 1 to n. You have certain gamma factor times L F cross Fs, which is resembling the functional equation of the Riemann zeta function very precisely. And the assumption that F is self-dual, which enables you to handle the coefficient of the Virtual series to be non-negative, which is somewhat necessary in several applications. Okay, next page, please. So one needs the bound for the conversion factor in principle. So here in the whole talk, we assume that F is self-dual, and our functional equation reads as lambda F cross Fs is nothing but lambda F cross F 1 minus S, and this is nothing but this product times L F cross S. S is nothing but this quantity times this product L F cross F 1 minus S. So if you write this functional equation in the following form, next page please. Chi F cross Fs times L F cross F 1 minus S as L F cross Fs. This factor is called the chi factor is called the conversion factor, which is nothing but the quotient of these two quantities, which can be estimated using the asymptotic formula for gamma function, where sigma varies over any fixed vertical strip as long as t is sufficiently large. If you use that asymptotic formula for gamma function for any complex variable with real part of S is in a fixed vertical strip, and imaginary part of S going to infinity. Next page, please. One observe. Okay, next page. These are all some calculations. So gamma function asymptotic formula we are using. More precise. Next page, please. This conversion factor is controlled by the bound mod t power n square times 1 over 2 minus sigma. So this is in principle, if you have an L function which is of degree n, then the conversion, and suppose that L function satisfies a functional equation of the Riemann zeta type, then the corresponding conversion factor behaves like mod t power the degree times 1 over 2 minus sigma. This is a very general fact. And hereafter, throughout the talk, we assume that n is always greater than or equal to 3. That means we want at least two components, V1, V2, of the type of mass form what we take. That's what we are interested in. Next page, please. The first lemma, what we observe here is that as long as my real part of S is bigger than or equal to n plus 1, the Rankin-Selberg L function LF cross Fs is absolutely convergent. Okay, this is a kind of an easy observation. In any case, let me just give you some idea how it is being done. So, by the definition of Rankin-Selberg in this case, this is product of zeta ns times this multiple different series. And what we do is that we rewrite this Rankin-Selberg function as zeta ns times sigma m is equal to 1 to infinity hm divided by m power s. Here hm is the number of representation of the integer m as product of this quantity m1 power n minus 1, m2 power n minus 2, etc. m1 minus 1 with the weight mod a m1, m2, etc. m1 minus 1 square. This is what hm means. Next page, please. One observes that it is already known for all non-zero integers m1, m2, etc., m1 minus 1, this quotient in absolute value is bounded. Thus, if you take the square, modulus A of m1, m2, etc., m1 minus 1 square is bounded by this product, which you can expand and then simplify. If you simplify, this is nothing but m power n minus 1. According to you, m is nothing but m1 power n minus 1, m2 power n minus 2, etc., mn minus 1. So this whole power n minus 1, that's what you need. Next page, please. So you have a bound for this Fourier coefficient square in absolute value. You just fix it up here. So this tells you that this multiple Dirichlet series is nothing but product of this individual Dirichlet series. Here, each individual Dirichlet series is absolutely convergent as long as the real part of S is bigger than n plus 1. So the first factor zeta ns, if you see, that is absolutely convergent in real part of S is bigger than 1 over n. And the rest of these factors is absolutely convergent in real part of S bigger than or equal to n plus 1. So in totality, your Rankin-Selberg function is absolutely convergent in the half plane real part of S is bigger than or equal to n plus 1. This is what you wanted to establish in lemma 1. Next lemma, please. Next page, please.
Sorry, something's gone wrong.
Why?
I don't know, but let me share it again.
Okay.
I lost your. Hang on. Hang on, sorry. Yeah.
Next page, please.
Okay.
Okay. The next lemma is that you would like to have a uniform bound as long as the real part of S lies in a fixed vertical strip. That means the real part of S is between minus n and n plus 1. So the uniform bound, what we claim is that this Rankin-Selberg is controlled by mod t plus 10 whole power n square by 2 times n plus 1 minus sigma. This estimate is uniform as long as sigma lies between minus n and n plus 1. The proof is standard. On the line n plus 1, the previous lemma tells you that Rankin-Selberg function absolute value is bounded. And using the functional equation on the line minus n, you can use the conversion factor growth, which we established using the symptotic formula for gamma function. And on the line n plus 1, bounded. So this tells you on the line minus n, this bound is true. You have on the right line, right side, right vertical line, n plus 1, you have a bound. On the left vertical line, you have left vertical line on the real part of S is called minus n. You have another bound. Now you can use maximum modulus principle to a suitable function and then estimate it carefully. This is what we do. Next page, please. We define the function fw to be the Rankin-Selberg LF cross f w e power w minus s whole square x power w minus s. Here x is an open parameter which might depend on t, which we will choose suitably. And once you define like this, one observes that as long as w is equal to s, f of s is nothing but Rankin-Selberg at the value s. So what we do is that one observes this kernel function e power w minus s whole square, which decays very fast exponentially on the horizontal lines, which enables you to kill the growth given by this function, so that on the horizontal line, the contributions coming from here, it becomes bounded. On the left vertical line, you have a bound. On the right vertical line, you have a bound. That means that the absolute value of the Rankin-Selberg function, as long as S is a point inside this rectangle, which is controlled by the contribution V1 plus V2 plus H1 plus H2. H1, H2 are horizontal line contributions. V1, V2 are vertical line contributions. Next page, please. Okay, it is shown that the kernel function absolute value, which behaves like exponential minus log t whole square, which enables you to kill h1 and h2. They behave like bounded quantity. v1 is nothing but which is controlled by x power n plus 1 minus sigma. v2 is controlled by mod t plus 10 whole power n square times n plus 1 over 2 x power minus n minus sigma. So if you glue all these estimates, next page please. This LFS, F cross Fs, this Rankine-Selberg absolute value is controlled by these three quantities inside. So X is an open parameter. The prudent way of choosing X is that these two quantities are of similar order. That tells you that you have to choose X to be mod t plus 10 power n square by 2, which tells you the uniform bound what we claim in that lemma. Next page, please. Okay, so from that uniform bound lemma, one observes that as long as real part of S lies between 0 and n plus 1, the Rankine-Selberg function is controlled by this bound in absolute value, that is mod t plus 10 power n square into n plus 1 by 2. Of course, this exponent is an integer that one should observe. The next lemma, what we would like to use is that this is a kind of a Perron's formula, not exactly, but this is a variant form of the Perron's formula, which tells you that this line integral is having a main term, namely 1 over k factorial times 1 minus 1 over y whole power k plus O of 4 power k y power c divided by t power k, as long as y is greater than or equal to 1. And whenever y lies between 0 and 1, this is O of 1 over t power k. Here c and y are positive real numbers. T is some arbitrary sufficiently large parameter will be chosen in the application suitably. So next lemma, next page please. Okay, our first theorem is the following. As I said, we are interested only when n is greater than or equal to 3, which is arbitrary positive integer greater than or equal to 3, but we fix it. For integers k greater than or equal to k0n is given by n square times n plus 1 by 2 plus n. This is our k0n. We fix n so that k0n is fixed as long as k is bigger than or equal to k0 in this case. This is called the kth Riesbein related to the coefficient of the Rankine-Selberg Bm. Sigma m less than or equal to x, Bm by k factorial times 1 minus m by x whole power k. You can see that m less than or equal to x, so this is the positive quantity. This has an asymptotic formula. This is what we establish here with a main term cx divided by k plus 1 factorial, and the error term is O of log x, and the f of this implied constant is depending on n, and of course c is an effective constant which depends only on the form f related to the Rankine-Selberg, whatever we defined. The main point here is that this error term is very neat, and this result is unconditional. Of course, this result is unconditional only when k is bigger than or equal to k0 again. This is very, very important. And this is called the kth Riesbein in the number theory subject. Okay, next page, please. Okay, for the lower level k, that is k less than k0n, one expects a similar kind of asymptotic formula. I will come at the end for this part. From the asymptotic formula stated in theorem 1, one observes that this sum is less than or equal to the sum, which is nothing but 1 over k factorial times summation m less than or equal to bm. So this tells you that this particular sum is greater than or equal to some constant depending on n times x. Of course, this constant will depend on f also, and this is true for sufficiently large x. Similarly, by considering instead of x 2x, if you take, you can get the other way inequality. Next page, please. The other way inequality will tell you that summation m less than or equal to x, bm is less than or equal to cn double prime x. Of course, cn double prime also depending on n and f in principle. So this tells you that the average value of this Rankin-Selberg coefficient is somewhat as like a constant. That's what it tells you in principle. But theorem 1 gives you more information, and it gives you very precise error term in this case, of course, for large level K. That is comparing to the dimension N. That's what matters here. Next page, please. The proof of theorem 1, little below. Hello? Okay. You take y is equal to x by m. You are going to make m less than or equal to x, so y is bigger than or equal to 1. That's what matters. And we take c is equal to n plus 1 in the variant version of the Parent's formula, so that 1 over k factorial times 1 minus m by x whole power k is nothing but this line integral plus this error term. This is what this follows from that lemma. Now you multiply by m, the coefficient, and then sum over m less than or equal to x. So precisely you get this sum bm by 1 over bm by 2 pi I, and then this line integral plus this error term. Of course, here you write only bm because, as I said, as long as I assume g is equal to f and f is self-dual, my bm coefficient is non-negative. Okay, so this is nothing but this line integral plus O of this, because anyway, you know that on the line n plus 1, my Rankin-Selberg function is absolutely convergent, so I can definitely change this integration and summation so that this Rankin-Selberg function can be introduced explicitly in this integral. Next page, please. So what we do is that we move the line of integration from real part of s equal to n plus 1 to 1 over log t. T is a positive parameter, large parameter, which we will choose suitably later. So this 1 over log t is very near to 0. That's what I mean. So this is the rectangle you have. Now you apply Cauchy's residue theorem to this rectangle. Of course, you know that the integrand contains the Rankin-Selberg function L f cross f s, which has a simple pole at s equal to 1, which will give you the residue. So all this sum of these line integrals along with 1 over 2 pi is nothing but the residue at s equal to 1 of the integrand. Next page, please. Indeed, this is what I said, 1 over 2 pi summation of all these 4 line integrals. This integrand is nothing but residue at s equal to 1 of this integrand works because LF cross Fs has a simple pole at s equal to 1. This is nothing but limit s tends to 1, s minus 1 times this product. So you just take the limit. The limit is nothing but constant times x over k plus 1 factorial. Of course, this constant will depend upon f. This is nothing but this limit. Next page, please. Now, this tells you that the right vertical line integral is nothing but the main term obtained from the residue along with the other line integrals in the opposite direction or whatever, opposite orientation, which is written. Next page, please. Yeah. So now I have to estimate the horizontal line contributions in absolute value as well as the left vertical line contribution in absolute value. So first one observes that the horizontal line contributions in absolute value is 2 times the absolute value of this line integral, which is this particular line integral, for instance, which is estimated to be, you can take the absolute value inside plainly, and then here x power sigma will come out. Sigma maximum is n plus 1, so x power n plus 1. Line and this length of this integral is at the most n plus 1, so n plus 1 comes. And of course, you have a uniform bound as long as sigma varies from 0 to n plus 1. So that bound comes from here. And the denominator, if you see, there are k plus 1 factors. Each one in absolute value is at least capital T that contributes T power k plus 1. So this is the bound. So you can multiply by 2. Anyway, that is included in the implied symbol. So this is the maximum contribution coming from horizontal lines, apart from the implied constant, computable in any case. Next page, please. The left vertical line contribution is nothing but this line integral. Hello, hello, hello. Lecture is going on. The left vertical line contribution is nothing but this line integral. You split into two parts, mod t less than or equal to t0 and mod t lies between t0 and capital T. Each integral can be estimated. Next page, please. So mod t less than or equal to t0, you estimate. Again, you pull this absolute value inside and then use the uniform estimate bound. And here the line is sigma is equal to 1 over log t. So x power 1 over log t comes. And here for the first factor, I take this as the lower bound. So 1 over log t comes. And for each other factor, I take 1, 2, 3, etc. That k factorial comes into the picture. So precisely, you estimate this to be nothing but x power 1 over log t times log capital T over k factorial, because the length of the integral is bound. T0 is some number, fixed number, positive number. So this integral is going to be some fixed number. So that number is put up in implied constant symbol. Next page, please. The other part of the vertical line integral is from mod t bigger than or equal to t0 and less than or equal to capital T. You again pull the absolute symbol inside, and then here x power 1 over log t comes into the picture. Absolute value, again you have the bound. And of course, here what we do, we take all the factors. There are k plus 1 factors. Each one these complex values in absolute value is bigger than or equal to t. So t power k plus 1 comes into the picture. And of course, you can integrate them precisely. And you can see that this is controlled by the bound t power n square times n plus 1 by 2 minus k plus 1 times x power 1 over log t. Next page, please. So in totality, this particular right vertical line integral is nothing but this main term, and these two terms are coming from the horizontal line contributions. No, vertical line contribution, and the other one is from horizontal line contributions. So, and this error term comes from the tail portion which appeared in the variant of the Parent's formula. So totally there are 4 error terms here with this main term that happens to be this K3 is mean. So now I am supposed to choose my open parameter capital T as a function of x in such a way that I get the minimal error term. What I do here is that I choose my T to be, say, x over 100, something like that. Next page, please. Yeah, I think I have written x over 10. Okay, so if you choose T to be x over 10 or x over 100, then precisely you see that all these 4 error terms, they are of this type. And you can easily see that this particular term dominates over all these other 3 terms. So precisely, whenever, of course, this dominates as long as k is bigger than or equal to k0 n. That is very important. Once you do that, you observe that your K3 is mean is having such a main term plus a very precise error term O of log x for all integers k greater than or equal to k0 n. This result is unconditional. So now the question arises, what happens to k less than k0 n? Okay, we could show a conditional result for lower level of k, but that conditional result holds good for all integers k greater than or equal to 1. That is another important criteria. So next page, please. Yeah, to prove the conditional result, what we do here is that we make 2 hypotheses. The first hypothesis is something called coefficient growth hypothesis. This is nothing but for every positive epsilon, the Fourier coefficient in absolute value is controlled by the bound m power epsilon. Here m is this product. One can view this coefficient growth hypothesis. This is slightly weaker than the generalized Riemann conjecture. The generalized Riemann conjecture tells you that the quantity complex numbers which appear in the monic polynomial, which I explained in the beginning, whose absolute value is 1. This is what the generalized Ramanujan conjecture says, which is again open. This is true for every prime p and I is equal to 1, 2, etc. This particular bound is weaker than this anyway. We assume only this kind of hypothesis. The next slide, please. Next page, please. Yeah, hypothesis 2. This is something called Lindelof hypothesis for the Rankin-Selberg in our case, which says that for every epsilon greater than 0 and whenever real part of s bigger than or equal to 1/2, the Rankin-Selberg function is controlled by the bound mod t plus 10 whole power epsilon, which holds good for sufficiently large t. This is the hypothesis 2. Of course, one expects this to be true, but we don't know. So, if you assume hypothesis 1 and 2, and as long as n is bigger than or equal to 3, then for any positive integer k greater than or equal to 1, all that we could show is that the general k is being for every positive integer k greater than or equal to 1 satisfies such an asymptotic formula with an error term O of x power 1/2 plus epsilon. Of course, the O constant depending on n and epsilon here. Of course, you can see the error term is weaker, but this holds good for every integer k greater than 1. This is what I wanted to stress here. Next page, please. A few lines about the proof here. The hypothesis 1 enables you to ensure that the Rankin-Selberg function is absolutely convergent in real part of s bigger than or equal to 1 plus epsilon. In the unconditional case, we had n plus 1 here. You should recall, and the error terms are controlled for every integer k greater than or equal to 1 by the Lindelof hypothesis for Rankin-Selberg function. So what we do, assuming these two hypotheses, you instead of moving the line of integration to 1/log t, we move the line of integration to real part of s is equal to 1/2, and the arbitrary parameter capital T is being chosen to be x power 1/2. And if you follow the ditto arguments in the unconditional case, this will lead to what I said in the conditional case. Okay, I think I am through. Next page, please. I give you a few references related to this work. One is Goldfeld. It's a very good book which explains a lot about Rankin-Selberg function, Godwin-Jacobi function, and so on. And of course, here you have Ingaum. This is a standard nice book. Jacques Shalika, of course, we have used. Jiang Liu, the Kim and Rudnick are not these papers I have referred in any case. And these are some two nice papers from which there are some ideas which we have used. And next page, please. So thank you very much for your kind attention. Thanks a lot. Is it okay, Atul?
Yeah. Thank you, Professor Sankaranarayanan, for the nice talk. Yeah. Any questions? Okay, so I had a question. So
yes,
just like the Lindelof hypothesis, is there a version of Riemann hypothesis for this function?
Yeah.
Okay.
Tell me. I couldn't hear.
Oh, I was saying if there is a version of Riemann hypothesis for this function as well.
Hello.
What happened?
Oh,
Atul, I couldn't hear.
Are you able to hear me? No.
Sorry, we can hear you.
But I'm able to hear Atul, sir. Yeah.
Atul?
You are not able to?
Yeah, like I can hear you.
I couldn't hear.
Yeah, Atul, sir. I can hear all of you actually.
Yeah, you can type on the chat.
Okay.
Can you check your chat?
No. Yeah. Can you hear me? Hello?
Yeah, we can hear you.
You can hear. Okay, yes. You expect a Riemann hypothesis like this for the Rankin-Selberg also. Yes.
Any other
As
question?
long, yeah, as long as you have an Euler product and a functional equation of the Riemann zeta type, you can expect something like Riemann hypothesis for the
Okay.
corresponding L function. Yes, one expect, but we don't know.
Right.
Okay.
Vivek, you had a question?
Yes. So, Professor Sankaranarayanan, thank you for wonderful talk.
Okay,
And
great.
So, yeah. So you have mentioned one Rees type property where you have said that K should be bigger than equals to K naught.
Yes, yes.
So,
Because I wanted to make all other three terms smaller than O of log x. That is
yes.
ensured
Okay.
only when k
Uh-huh.
is sufficiently big
Mhm.
comparatively to n square times n plus 1 by 2 plus n. Otherwise, I cannot do.
Okay.
So
Okay.
the result
I
becomes
see.
unconditional whenever k is somewhat larger comparing to n cube or whatever you call. Yeah.
Okay.
For smaller
So,
k, I have to assume this hypothesis, or otherwise I cannot do anything with the error term. Error term dominates.
oh, okay. Okay. I see.
Hi, may I ask a question?
Sure.
Yes, please. Yeah.
So, in the case of classical Rankin-Silberg problem, so for example, if you take n equals to 2,
Yes.
like have people considered it, or what is the state
Yes,
of art?
n equal to 2 is something like one dimensional, right? N minus 1 only you are considering, right? The type V, if you write just one component is going to be there, right? Hello.
Yes.
So that is a simple matter in principle.
So, in that case, like all the Rees means have been studied, right?
Yeah, it can be done. It is easier.
So, yeah, for example, if you take two holomorphic forms,
Yes,
and
you
then
can do it.
their
You can
Rankin-Silberg.
do it. You can do it. Definitely one can do it.
Okay. Thanks.
Sir, I have one more question.
Yes, please.
Suppose even in the classical case or for this Rankin-Silberg function, if I
Yeah.
want to study the summatory function of higher power of the Bn, what is the
Yes.
coefficient of the Rankin-Silberg?
Yes.
So, are there any such kind of results in the
As long
literature?
as long as you can associate an L function corresponding to the higher power of the coefficient,
Yeah.
you will
Okay.
be able to handle
Okay.
the show.
Okay.
That will be the
I
tricky
understand.
part.
Yeah, that is the tricky part.
There
Yeah.
you should be able to cook up something, or
Yeah.
at least you should be able to write as a product of some nice L function
Yes.
times
Yeah.
some easier
Yeah.
factor which you can handle.
Okay.
Then also you can
Okay.
handle.
Okay. Thank you.
Okay, great. So Krishnan Rajkumar, nice seeing you on the screen.
Hello. Yeah, sorry, I got a little delayed.
It's
Thank you very
okay.
much for giving the talk.
Okay, great. Thanks a lot.
Are there any further questions?